Okay, in this video I'm going to review the notion of relation and equivalence relation. It's found in your appendix on page A-9. And relations should be familiar to you from elementary school, high school mathematics. Less than and equals, greater than, these are all examples of relations. Formally, we define a binary relation as follows. Binary relation applies to a set. In this case, we're calling the set A. And the binary relation is defined as a set of ordered pairs of elements of A. Okay. For example, some elements of the set that is the relation less than are 3, 5, 3, 7, and 1, 100. Why are these pairs elements of less than? Because 3 is less than 5, 3 is less than 7, and 1 is less than 100. Okay. In this example, he didn't specify what the set A was. We could take, in this case, the set A to be natural numbers. So we can identify this relation less than with the set of all possible ordered pairs such that the first number is less than the second number. Right? It's a different way of thinking about less than, but if you think about it, it's just a different representation of the same concept. Okay. Another binary relation on the natural numbers is equality. Okay. All right, this relation is the set. Actually, he shouldn't be saying natural numbers here. He should be saying integers because he's doing -1 here. If you take all ordered pairs such that the first number in the ordered pair is equal to the second number of the ordered pair, that represents the relation equality. Right, you could actually graph that in the plane. Right? If you graphed this set of ordered pairs for the integers, you get all these points on this line here. So this is actually another way of representing relations, is by a graph, by a two-dimensional graph. Now these are all different representations of the very same concept. Okay. Now another example is closer than 10. Okay. If I take two numbers x and y, if x minus y, the absolute value, is less than 10, then that pair of numbers is considered to be in this relation. Okay. So we're identifying this relation closer than 10 with all pairs of numbers that satisfy this condition that they're closer than 10. And of course, 11, 1 and 1, 11 are not numbers because they're not closer than 10. The distance is equal to 10. Okay. All right, so these examples illustrate the generality of the definition. And here's some other possible relationships between numbers. Both numbers are even, or the first number is the second with the digits reversed. These are all covered. Okay. One special type of relation expresses similarity between two objects. Now here we say two objects, but really we're thinking about numbers or numerical, perhaps vectors, something that's something that's mathematical. We want to define equivalence relations in such a way that they reflect the fact that the two things that are related have some similarity. Right? For instance, in geometry, you talk about two geometrical figures being similar. They aren't identical, but they're related. Okay? Here's another example. If I want to express the fact that two integers have the same remainder when divided by 2, then those two integers are related in some way. Right? So here are some additional conditions that an equivalence relation must satisfy. First of all, an equivalence relation must satisfy the condition of reflexivity. Any object is related to itself. Now we'll give examples in a minute, and you'll see how this works. 2 is symmetry. If A is related to B, then B is related to A. And 3 is transitivity. If A is related to B and B is related to C, then A is related to C. Now you can certainly see these three things are true for the relation equals. Certainly, any number, no matter what set it's drawn from, is equal to itself. Second of all, if A is equal to B, then B is equal to A. And we use this fact all the time in algebra. And transitivity, if A is equal to B and B is equal to C, then A is equal to C. So this certainly is satisfied by equality. Now, if you think about it, another example of an equivalence relation would be, where is it? This one here. The equivalence relation on integers. Two integers are equivalent if they give the same remainder when divided by 2. All right, so that's my new relation. It's a relation on the integers that two integers give the same remainder when divided by 2. And you can go through these three conditions and verify that this relation is reflexive, symmetric, and transitive. Now, I invite you to look back in your algebra book or your discrete math book. I'm sure you can find many examples of equivalence relations. Okay. Another possible relation on the integers would be same sign. We say two integers are related if they have the same sign. Well, you can see all of these ordered pairs belong to this relation. 1 has the same sign as 3, minus 5 has the same sign as minus 7, 0 has the same sign as 0. You can show that this relation satisfies these three conditions. Certainly any number has the same sign as itself. If A has the same sign as B, then B has the same sign as A. If A has the same sign as B and B has the same sign as C, then A has the same sign as C. So this same sign relation is an equivalence relation. Now, in this case, there are actually three types of pairs. We have the pairs where both numbers are positive, the pairs where both numbers are negative, and one pair where both are 0. So integers fall into exactly one of three classes, positive or negative or 0. Okay? So what we're saying is that integers can be divided up into three disjoint sets. This is called a partition. In general, a partition of a set omega is a collection of subsets such that every element of this should be omega instead of S. It should be omega. Okay. Every element of omega is an element of a subset which is one of these S's. Okay. All right, he forgot the S0 here. All right. And this should be omega here. Okay. So, and overlapping parts are equal. So if Si intersect Sj is not empty, then Si equals Sj. Okay. So here's a picture of omega. The words here are a little confusing, but just remember the picture. This entire set is the set omega. And it's divided up into disjoint sets that comprise the entire set. So that's a partition. All right, in the prior paragraph, the same sign partition the integers into positive, negatives, and 0. The equivalence relation equals partitions the integers into one element sets. Okay. Now, one thing about this partition is that if I take any two elements, in S1, all right, so let me go backtrack and say this again. In the same sign partition, there were three sets, right? There was the positives, the negatives, and then there was a single element set 0. Now, any two positives were equivalent. Any two negatives were equivalent. They have the same sign. Okay? So there's a close relationship between partition and equivalence relation. Okay? Every equivalence relation creates a partition. And on the other hand, it's true that every partition creates an equivalent relation. So they're very closely related. Let's look at this example. Is the set of strings consisting of a number followed by a slash followed by a non-zero number. Okay, so here we have omega is equal to some number, and that number is an integer, divided by a non-zero number, d, where d is non-zero. And we can define a set which is defined on this set of strings. They say that two strings are equal if the well, this is the usual cross product to show that two fractions are equal. Okay. So we can check that this is a partition of omega. Okay, for instance, S of 4, 3 equals S of 8, 6. You can show that 4 times 6 equals 3 times 8. Okay, and this shows some numbers in each subset of the partition. Now notice that what we're saying here is we're showing how to identify equal fractions. Okay, every pair of numbers in this partition represents an equal fraction. Every pair of numbers in this partition represents an equal fraction. Okay. All right, so here he's saying what I indicated before, that every equivalence relation induces a partition, and every partition is induced by an equivalence. Okay, and here we have some particular examples. You can read through these examples here. Okay. So we call each part of a partition an equivalence class. As I mentioned, we can think of everything in one of these partition sets as equivalent to each other. Okay. We sometimes pick a single element of each equivalence class to be a class representative. Sometimes there's a particular element in each partition that is distinguished in some way and represents all the elements in our class. One example, for instance, in our example of the two pairs that represent the same fraction, we can choose the pair of numbers that represents the fraction in lowest terms. For instance, 4/3 is the same as 8/6, so 8/6 is also in this set. 12/9 is also in this set, but there's only one representative in this set that's in lowest terms. Okay, and that's going to be our representative. Okay, so that's a brief introduction to equivalence classes. Again, you can go to a text in discrete mathematics or go on the web if you want some more examples of this.